Welcome to STEM Baba. In this video, we'll discuss the problem and conceptual exercises of chapter 4 from the book James's Walker. So let's start. So in this question, we are given that a football player kicks off a football and it lands into the bucket. Now this horizontal distance is 45.70 meter. Now the ball is launched at an angle 38 degrees above horizontal. This is launched at an angle 38 degrees above horizontal. Now we are asked to find the initial speed needed so that the ball lands into the bucket. So let me first show the trajectory. So this would be the trajectory. It will go up, reach the maximum point, and the football will come down, and then it comes to the bucket. So we are asked to find the initial speed V0 for the football. Now this is basically what this is the range, and we can consider that the bucket is placed at the same level from which the ball is thrown. Okay, now for this kind of situations, when the initial and the final elevation is same, we have derived the formula for range. And if you haven't seen that video, please go to my previous video where I have derived these formulas. Okay, now range, we derived the formula to be R equals to V0 square over G times sine 2 theta. Now theta we are given to be 38 degrees. Range we have G, it's a constant 9.81. V0 we can find it from here. So from here the expression for V0 will be equals to under root G times R over sine 2 theta. Now simply we have to put the values to find the answer. So under root G is 9.81 meter per second squared. R is 45.70 meter divided by sine 2 theta. So 2 times 38. So that will be equals to 21.50 meter per second. Thus, the football should be hit with a speed of 21.50 meter per second such that it can land into the bucket. So this for the answer for the A part. Now next in the B part it says, by how much would the launch speed have to be increased if the bucket is moved 46.50 meter downfield? So if this bucket is displaced from this position to here, such that this total distance now becomes 46.50 meter, then what would be the increase in initial speed? So we're going to use the same formula to calculate the initial speed required for this distance, this range. So this is the B part. So V0 will be under root, same formula. G is 9.81. R this time becomes 46.50. Angle is same. So sine 2 times 38 degrees. And that is equals to 21.68 meter per second. So what is the increase in speed? Delta V. Simply you have to subtract these two values. So 21.68 minus 21.50, which is equals to 0.18 meter per second. Therefore, the increase in speed should be 0.18 meter per second such that the football lands into the bucket. So this question is based on volcano eruption. Now the lava ejected from the volcano goes to a maximum height of 2.00 times 10 to the power 5 meter. This is the maximum height, H max. And all this stuff is happening on a place called Io, a moon of Jupiter. Now the value of G on Io is given to be 1.80 meter per second squared. Now we need to find the initial speed of lava. So what the question is saying, a lava is going up with some initial speed V0, we don't know. It reaches to a maximum height, and this maximum height is H max, that we are given to be 2.00 times 10 to the power 5 meter, and then it comes back. So initial speed we have to find. Now since the lava goes straight up and then straight down, so we can use the equations of motion in the vertical direction. So we can write that Vy square is equals to V0 y square minus 2g delta y. Now at the highest point, this Vy becomes 0. So this is 0, and V0 y is the initial speed that we have to find. minus 2g delta y, and delta y in this case it will be h max. So we can put the values now. This is 0 equals to this thing we have to find, minus 2 times j is 1.80 meter per second squared. Delta y is h max, and h max we have the value, we can put it directly now. So 2.00 times 10 to the power 5 meter. We can solve it for v naught from here. So v naught y, it comes out to be as 849 meter per second. So this is the initial speed of the lava. Now in the question B, it is asking that if this volcano were on Earth, would the maximum height of the ejected lava be greater than, less than, or same as that on the Io? Now we know that the acceleration due to gravity on Earth is 9.81 meter per second squared, which is far larger than this value, this one. So if the launch speed remains the same, the maximum height of the ejected lava on the Earth would have been less, because the value of g on the Earth is very high as compared to this. So the answer would be, the maximum height would be less on Earth. Now in this question we are given that a soccer ball is kicked with an initial speed of 8.25 meter per second. So v naught we have 8.25 meter per second. Now after 0.750 seconds, the ball is at its highest point. Now we need to find the initial direction of motion. So the ball is kicked at some angle that we have to find. Let this be theta. Now after time 0.750 second, it reaches to its maximum height and then it goes down. So at the maximum height, we know that the vertical component of velocity becomes 0, because the ball is traveling like this at this point. So Vy is 0 at the highest point. So we can use the equations of motion in the vertical direction, which is Vy is equals to V naught y plus Ayt. Now v naught y is the initial speed in the vertical direction, which will be v naught y is v naught sine theta, and ay we have minus g, right? Because we always consider this direction to be positive y and this direction to be positive x. So g is always downward, so that is why ay is negative. Okay, so Vy is becomes 0, v naught y is v naught sine theta minus gt. Now from here we can write that sine theta is gt over v naught, or from here we can write that theta is sine inverse gt over v naught. Now g we have, t we have, and v naught we have. We can put the values to find the answer. So theta is equals to sine inverse, g is 9.81 times the time taken by the ball to reach at this point is 0.750 seconds. So 0.750 seconds divided by v naught is 8.25 meter per second. On solving, we'll get the answer to be 63.1 degrees. So in this question, we are given that child 1 throws snowball horizontally. So one child throws the ball horizontally, and another child throws the snowball straight down. So it throws straight down like this. Now once in flight, is the acceleration of snowball 2 greater than, less than, or equal to the acceleration of snowball 1? Now basically after the release, after the projectile is released, the only acceleration on the projectile is acceleration due to gravity. It doesn't matter it is thrown horizontally or vertically. So the acceleration will be same. It does not depend on the direction, which is 9.81 meter per second squared. Very simple question. Now in this question we are given that a dolphin leaps from water with some speed. Now we need to figure out at the instant a leaping dolphin lands, its speed is greater than, less than, or equals to the speed when it left the water. So suppose the dolphin left the water with some speed v naught, then what would be the speed when it comes back to the water? This is what the question is asking. Now we can consider the dolphin to be a projectile where the launching and the landing altitude is same. And when we discuss the key characteristics of projectile motion, I told you When the initial elevation and the final elevation is same, then the launching speed and the landing speed is same. Thus, it will land with the same speed with which it was launched. Answer would be that this will be equal because of the symmetricity of projectile motion. Now, this question is connected with the previous problem, and I will discuss both the problems one by one. First, we will discuss the previous problem and then we'll get back to this question. So here you can see two images. Now for this image, the elevator is at rest. So this is at rest, and in this case the elevator is moving straight up with some velocity, say V0. So now here a person standing flips a coin in an elevator that is at rest. So the coin goes up and then it come back to the ground. So let the time of flight be TR. Now in this case, when the elevator is moving up with some constant velocity V0, now here also the person tosses the coin and it goes up and then come back to the ground. So let the time of flight in this case be TC. Now we need to tell, is the time of flight in this case for the coin is same as in this case. So actually the answer would be that the time of flight in both the case TR and TC will be equal. Why? And the reason is that both the coin and the elevator are moving with the same velocity relative to Earth. So the coin's velocity relative to the elevator is 0, and the outcome of the experiment is exactly the same as when both the coin and the elevator are initially at rest relative to Earth. So for this case, the time of flight for the coin is same. But now in this question it says, if this time the elevator is moving with some acceleration, let it be A, then will this TR and TC will be same or not? So pause the video and think. So in this case, when the elevator is moving with some acceleration, the time of flight for coin is less than the time of flight when the elevator was at rest. And the reason is the second option. This one is the reason. It says that the elevator's upward speed increases during the coin's flight. That is true because there is acceleration, so every time the speed is increasing when the elevator is moving up, and hence it catches up with the coin at a greater height than before. So since this elevator is moving up with some acceleration, then the coin will reach to the ground or to the elevator's floor in less time. That is why the time of flight for the coin is less in this case as compared to this case.